Happy day and welcome everybody. So what we're going to be talking about today is bond enthalpy, bond energy or bond enthalpy. Okay, so what is this word? What does this mean? Well, we know that enthalpy simply refers to like our delta H or our change in energy. And so all that's going to happen is we want to see like how much energy is required to actually separate and pull apart an actual bond. Okay, so we talk about IMFs, intermolecular forces. That's not what we're talking about here. So we're not talking about the energy that it's going to take to actually separate, for example, two water molecules to turn it from a liquid into a gas. That's not what we're doing. We're actually breaking a bond. Okay, so the strength of a covalent bond between two atoms can be used to determine the stability of a molecule. So how stable it is, the bigger the number is going to be, obviously, then that's going to be more stable. So the bond energy or bond dissociation energy is the amount of energy needed to, anybody can unmute. What are we talking about? What are we doing here?
Breaking it apart.
We're breaking it apart. I like it. So we are going to break 1 mole of gaseous substance. So this is the same as delta H of a reaction if we were in the thermo unit. So I want to make sure you understand this. There are different ways that you can calculate delta H. So one of the ways was using calorimetry. Okay. One of the ways was, and that was experimental. Okay. Another way is if you know your delta HF values, you can do products minus reactants, and that's going to give you delta H. Okay. Another way that you can figure out your delta H is if you know every single one of the bond enthalpies for all of your bonds within every single molecule in your chemical reaction, then it's a little bit different, because instead of doing reactants, products minus reactants, it's always products minus reactants. What we can actually do now is reactants minus products. And that's basically all we're gonna do. It's pretty easy, okay? And so we can see here that we have a molecule up here, AB, and then it always requires energy. So it does require energy. And so since it requires energy, if I were to write this as a delta H value, my bond enthalpy is a delta H value, bond enthalpy is always going to be, my delta H is always going to be positive. Okay, so it's always going to be a positive number. You will never have a negative bond enthalpy value. Okay, and so then you can see that it breaks apart into A and B on the other side. Okay, so this is the same. Okay, so we've got H2 turning into 2H, and we've got our delta H value of a positive 436. Why? What happened? Well, we simply took our HH that was together and we split it apart into two separate H's. Okay. Now, if you reverse that reaction and instead you bring them both together again, notice instead of being a positive sign, it's the same number. Instead, it's negative. Okay. So pulling them apart is going to be always positive, and then putting them back together is going to be negative. Okay. Now, your entire reaction, though, is dependent on the sum of how much energy does it take to break all of your reactants apart, and how much energy does it take to put your products back together when you reform new bonds. And so when we do an entire reaction, that doesn't have to be positive or negative. That can be either one, depending on your accounting. Okay, so that's basically how that's going to work. So let's compare CO. Now, I want to make sure you understand that, because sometimes people will say, oh, well, it's carbon and oxygen, it's always going to be the same. It's not. Why? We need to make sure we do our Lewis dot diagrams so that we can see, is it a single bond, is it a double bond, or is it a triple bond? Okay. The single CO bond, it says, is 358. And this is up in kilojoules per mole. Our C double bond O is going to be 799. And then we've got 1072 for our C triple bond O. Okay, so obviously somebody unmute. Which one is the strongest?
The triple bond.
The triple bond. Somebody tell me a reason. Why do you think the triple bond, which is the C triple bond O, why do we think that that is probably the strongest?
It's three electrons that are being used to hold the atom together instead of just
very
two.
good. 3 bonds, which means a total of 6 electrons are shared between. 6 electrons are shared in between. Okay, very good, which means it's going to require more energy to separate it, right? And there's also what happens when you have 3 pairs of electrons in between. What happens to your actual bond? It becomes, anybody want to guess? Is it a longer bond or is it a shorter bond if you've got a triple bond?
It would be a
Sure.
short bond.
Yes, it's going to be a shorter bond. Awesome. So this is also going to be a shorter bond. Okay, so it's being held more closely together, and so that will end up being a shorter bond. Okay. Some things to keep in mind. So the stronger the bond, what do we think? The greater or the stronger the bond energy. Okay, so the stronger the bond, the greater the bond energy. Bond energy of multiple bonds is greater than bond energy of single bonds, just like we said. So if you have like a triple bond, that's going to be a stronger bond enthalpy than a double bond, which is going to be stronger than a single bond. And I'm purposely drawing it longer. Okay. Energy is always required to break bonds. Again, that means that my delta H is going to be positive, will always be positive for this, for bond enthalpy. And energy is given off when the bonds reform. Okay, so then delta H would be negative in that case. And then we have the greater the electronegativity difference. Oh, this is important. The greater the extra bond energy. So we know that electronegativity difference is simply looking at, like, for example, fluorine is a 4, okay? And so what you can do is you can almost even estimate, if you're looking at a periodic table, you can basically estimate to say, okay, let's take a look here and say, okay, well, I know fluorine's here. And if they said, which one has a bigger like bond enthalpy? If I had fluorine bonding with chlorine, or if I had fluorine bonding with like hydrogen, for example. And so if you have a bigger bond enthalpy, a bigger difference, then you should have a greater bond. If their electronegativities are greater difference, then your bond enthalpy should be also greater. Okay, so the other thing is, so we can see that HH is 436 kilojoules for every mole, and FF is 153, and then we've got HF at 565. Okay, what I wanted to show you with this was, if you have HH and FF versus the HF, you're going to see that this is going to be a greater bond enthalpy difference, again, when we have a greater electronegativity difference between them. Okay, so what are we going to do? We are always going to do the sigma, or we can just say reactants, our delta H for our bond enthalpy, and I'm just going to call it BE, is equal to, and just put reactants minus products. Okay, so this is the only time that we're going to do backwards. Okay, because we want broken minus formed, we're going to do it backwards. Okay, all right, so pretty easy. All we're going to do here is we are going to draw our Lewis dot diagrams for every single one of these. So let's pause for a second so that you can kind of get your Lewis dot diagrams going. And then we will figure out what our bond enthalpies are. Why? Because a single bond is different from a double bond, is different from a triple bond. Okay. All right. So if you want to try it on your own while I'm working it out, then we'll go ahead and do that. So I do want to circle my coefficients, by the way, because that's going to be really important that I don't forget that, because I'm going to have to multiply by that. So I'll come back over and do this in a second. So I've got CH3OH, and I can even add up my valence electrons right here. I know that carbon is 4, and each hydrogen is 1. So I have 3, and then oxygen, I get 6, and then another hydrogen is 1. So I'm getting a total of 8 and 6. I'm getting a total of 14 on this one. My oxygens I know are 6 times 2, so that's going to be 12. Carbon again is 4, and each oxygen is 6. So 4 plus 12 is giving me 16. And by the way, some of you already know like what the what oxygens look like, or what carbon dioxide looks like, and then we know that water. We already know what waters looks like, and so again, that's going to be 8 valence electrons. Okay, so CH3OH, the one that's going to go in the middle, is going to be my carbon is going to be the one that is going to go into the middle here. So I have CH, hydrogens have to go on the end. And then remember, this is not an acid. This is not an acid, okay? It is OH, that's not a hydroxide group though, okay? So keep that in mind. So this is an alcohol, and I always like to remind people of that, because as we go through and start working on exams and stuff like that, sometimes that will come up. Okay, so I know I have 14 valence electrons, so far I have 2, 4, 6, 8, 10. So where do my other ones go? Well, they're going to go on the oxygen. And I'm not doing the shape, but just an FYI, because you do need to know this. Okay. If we were to do the hybridization around any of these atoms, I could figure that out. And simply just by saying, like, for example, around this carbon right here, I would say it's S, sp, sp2, sp3. So that would be sp3. And I did want to mention this because sometimes this question will come up on AP exams and students didn't understand what was going on with this. So then if I do the oxygen that's right here, then I would do S, sp, sp2, sp3. So far, these are both sp3, okay? What you would say is, since they're both sp3, you would say that they're in the same plane, okay? So sometimes you'll hear that, like, which one of the following has the electron domains or something like the atoms are not arranged in the same plane, okay? So if you hear that, that's what they're talking about. Okay, the other thing that I wanted to mention is if they asked you for the shape, okay, if they asked you for the shape, yes, around the carbon, it's got 4 bonded. And so somebody unmute. If there's 4 bonded with no lone pairs of electrons, what shape should that take on and what should the bond angle be?
Tetrahedral. And
tetrahedral. And then
One-
anybody remember what the bond angle would be?
I believe that's 109.5.
Perfect. It is 109.5. Awesome. Okay, now around the oxygen, we have 2 lone pairs of electrons. And so if you remember, if it's got 2 bonds and 2 lone pairs of electrons, somebody unmute, what should that shape be? Around just the oxygen, not around the carbon.
That would
So-
be bad.
It would be bent. Awesome. That would be bent. Okay. So if you have 2 lone pairs of electrons, then it's going to be bent. And remember, that's going to push them closer together. So you should get your smaller bond angle where it could be 120 or it could be 109.5. So that's how you would figure that out. All right. Okay. Let's go back to bond enthalpy. And then again, I want to make sure that I put my 2 in here because there are 2 of them. Okay. Then, and you can do like parentheses if you want to. Oxygen. Will you guys remember? Oxygen is just going to be O double bond, and then we have our electrons around it. So remember, oxygen is the only diatomic that double bonds. Now I have carbon dioxide. Anybody remember carbon dioxide? Because I know that tends to come up quite a bit. What does carbon dioxide look like? All single bonds, double bonds, triple. What's the best way to do carbon dioxide? Anybody remember this? So if you do CO2, you want to remember it's actually 2 double bonds, okay? And carbon dioxide, remember we exhale it, very important to living things, right? So plants need carbon dioxide, so really important to remember this. And then we just have, if you're doing Lewis dot diagram, it would simply look like that. And we have 2 of these. My 2 here, I forgot to put my 2 in there. Put 2 in there. Okay, so 2 carbon dioxides, and the last one is waters. We remember water, and I always draw water, even though you don't have to. I always like to draw it in its bent shape, just so that we remember. And so there's water in its bent shape, and we have 4 of them. Okay, so now all we have to do is our accounting system. So what we're going to do is we're going to use our bond enthalpy values. And so I have some here, and they're not always exact. So you have your reference sheet, and so you can use the back of your reference sheet, which I believe I tried to get the ones that are similar. So this is what you can be looking at when you're working in the breakout rooms to work this out. Okay. So let's come back over here and let's try to see if we can figure out what these are. Okay. So somebody unmute, and hopefully it's going to be somebody new. What I want you to tell me is, what bonds do you see? In other words, if I'm trying to figure out here, do I see an NH bond? Do I see an N double bond O? Do I see a CN? So somebody tell me, what do you see in this methanol, the CH3OH?
3 CH bonds,
I like it. Okay, so let's start there. So I've got,
a CO bond, and an OH.
perfect. Okay, I've got CH bonds. I have 3 of them. So 3 of the CH bonds. And then I heard there's also an OH bond. And what else do you see? There's one more thing that I see.
The CO bond.
And the CO bond, perfect. And 1 CO bond, and that's a single bond. Okay, now I want to make sure that I incorporate the correct number. So I do have to multiply, because this is 2 here, I do have to multiply all of these by 2. So instead of 3 CH bonds, I'm going to make that a 6. Instead of 1, I'm going to make it a 2, and then that one is going to be a 2, okay? The oxygen is pretty easy because it is just O2, and so we're going to write the numbers down in just a second, but I just have 3 O double bond O's on this one, and then over here for the carbons, I have 2 of the C double bond O's, but remember, I need to change that because it's 2 times that, so it's actually 4 of those. Okay, and then the last one is I have 2 of the OH bonds, but again, because I have, sorry, too close, because I have 4 of them, that's going to be 4 times 2, which is going to be a total of 8 of them. Okay, so now what we're going to do is we're going to get the numbers. So we're going to come down here. We're going to take a look at CH and OH. Let's see if I can remember. So CH says 412 and OH says 463. Okay, so I've got 412 and I've got 463. And then my CO bond. Oh, and then I'm going to tell you guys something after. My CO bond, I have a 360. For this one is 360. My O double bond O, so I am not using the single bond right here. It's not 157. So I'm gonna take a look. Oh, this one has the diatomics right here. So there's O2 at 496. Okay, so my O2 is at 496, and that was 3 of them. And then the last one is C double bond O. Oh, and then I already know the OH, but C double bond O is right here. I have a 743 for my C double bond O, 743. And then my OH already figured out on the other side was 463. Okay, you don't have to do this, but because right now, all you're gonna do is, and then remember, this is where your arrow is, okay? I really don't want you to write anything else down. What I would rather that you did is just went straight into your calculator and started entering the numbers in. So what I want you to do is just that. I want you to go ahead and I want you to start plugging the numbers in. And just an FYI on this, I do reduce by 1. Anybody want to tell me what you see that's on both sides that we can actually cross off?
OH bonds.
Awesome. 2 of the OH bonds right here, I can cross off and instead make this 6. Okay, it doesn't really make that much of a difference because you're just plugging it into your calculator anyway. Okay, so what are you putting into your calculator? Okay, so hopefully what you're doing is you're doing 6 times 412 plus 2 times 360 plus 3 times 496. Okay, now come our minuses. Okay, so remember you add in this one, this is backwards, right? So usually we do products minus reactants. So now we're going to subtract the reactants. So far I have 2 plus signs. Okay, so now I'm going to do minus 4 times 743 minus 6 times 463. 6 times 463 equals. Okay, so now I will tell you that typically what we do is we go around the room and I start having people call out their numbers. Call out your answers. Go ahead, everybody, call out your answers. And I will tell you that usually I get about 5 or 6 different answers for this. What we want to make sure is that we all did it correctly. There is only one correct answer, okay? And I will tell you that it's negative and it's somewhere in the 1,000 region. Anybody want to unmute and tell us what you got?
Negative 1295.
Yes, that's correct. Okay. And hopefully if you didn't get that, so negative 1295, and our answer is going to be in kilojoules for this. Just double check that, make sure. So you can see here, just always to make sure that our units are right. And so we've got kilojoules, and I'm not going to say per mole because per mole is like per mole of what? Like, did I pick something? So it's not per mole, it's for this reaction. In other words, this is my delta H, that if I did products minus reactants using delta HF values, I should get the exact same answer. If I did calorimetry and ran this, in this case, it would be a bomb calorimeter, right? But if I did a calorimeter bomb reaction where I burned the methanol, I should be able to get the same amount of energy released if I did that as well, okay? So keeping that in mind. All right, question 2, I just, I tried to do one maybe with a little bit of a twist, but I don't even think, I feel like this one's like pretty easy to do. So let's go ahead and see what we can fill in. So try this alone. If you need to listen to me, fine. Otherwise, just mute me for a second and go ahead and see if you can figure it out by yourself. Okay. Okay. So I only have one CH4. I know it's 4 plus 4. I've got 7 times 2 for my chlorine, which is 14. For my fluorine, same thing. It's going to be 14. Carbon is 4. Fluorine is 14. And then my Cl2 is another 14. So I've got 28 and 4, which is 32. My HF is 1 and 7, which is 8. And then same thing here. That's going to be 8. So I've added up my valence electrons just to make sure I do my Lewis dot diagrams correctly. Okay, so I've got CH4. Oops. So CH4 goes right here, plus 2 of these Cl2s, and I know that's going to be a single bond, plus F2. And by the way, unless you're asked for this, which usually they'll ask you for this before you do bond enthalpy, but if you already know that it's FF, you really don't have to do all the dots. You would just write FF, right? Okay, so if I've got CF2Cl2, the carbon's going to be the one to go in the middle, okay? And so the way this is going to look is I'm going to have C, and then we're going to put our Fs on one, like opposite of each other, and our CLs opposite of each other. Okay, so I've got CL, and it doesn't matter which ones are on top and which ones are on the bottom. And I only have one of those. Oh, I forgot my 2s. 2 in front of this. Okay, there's only one of those. And then again, 2 on my HF. So it's going to be HF. That looks like that. We know H only gets 1. And then 2 of the HCl. And again, same thing. That's going to be my 8 on there. Okay, so now all I'm going to do is figure out all of my bond types on this. Okay, so on this first one, I see that it's just 4 CH bonds. 4 CH bonds. On this one, I have 2 CL-Cl bonds, so that's not changing. Same thing here, I have 2 FF bonds, and then I have my products. So I have 2 of the CF, and then 2 of the CCLs. And then on this one, again, I have 2 of the HFs and 2 of the HCLs. So this was a pretty easy one. And so again, all we're going to do is fill in all of our numbers for each one of these. I already have the numbers, like I already wrote down my numbers, so I'm just going to fill those in a different color. So I have 413 for this one. My CL is a 242. My FF is 155, and that's probably what like takes the longest, is just making sure you get your numbers right. My CF is a 485. My CCL is a 328. The HF is a 567, and the HCl is a 431. Okay, don't forget to multiply by these numbers. Okay, so let's see if you can go ahead and do your calculation. I'm not going to write anything down right now, so I'll just tell you, remember it's 4 times 413, 2 times 242, plus 2 times 155, minus the other ones, okay? You have to minus every single one of those. And then, so I'm going to give you guys a second to try that out in your calculator. So if you didn't get this far and you were still like drawing things out, that's okay. I really just want to make sure that you can do this calculation and that you're going to get the right answer. Okay, so after doing all of this, delta H for the reaction, and this is called delta H of the reaction now, okay? Those are bond enthalpies. Every single one of these are bond enthalpies. Those are BEs, but the total of the full reaction is still just called delta H of reaction. Okay, so you should be getting an answer again that's in the -1,000 something. Anybody already there?
Is it -1176?
Yes, it is. Very good. So you should get -1176 kilojoules for that answer. Again, just make sure that you retry, and then I'm going to take questions at the end too, after we're done with this too. So if any of you have any questions, then we can go over that too. Again, just making sure that it's reactants minus products. Quick question, somebody unmute. Or if you got the answer right, did you have to use parentheses?
You don't have to now.
Nope, you don't have to use parentheses, okay? And so this is really gonna save you a lot of time. So when you go to do your calculations, because there are people that are like, well, I'm gonna write this one down, I'm gonna write this answer down, I'm gonna write this answer down, write this answer down. You're taking way too long, okay? And so I wanna make sure that we're at a point where, yes, not only do you know how to do it, but you can do it quickly, okay? So that's kind of, I guess, half the battle on this. Okay, and last one on here is, again, using the table, calculate delta H for the following. Okay, so I like this molecule. C2H4. Why? Okay, so valence electrons, I've got 4 times 2, so I have 8 plus 4. So I have a total of 12. Oops, 12. I've got 12, I have 14. And then I have 4 times 2 is 8, plus 4, plus 14. So what do I have? 12 and 14, 26. Did I do that right? 26. I think that's right. Okay. Somebody unmute if I did that correctly. Okay, so now I'm going to set this up. So if there are 2 carbons, what do you think I have to do on this? This is kind of weird.
You bond them together.
Yes, they are going to be bonded together. So I'm actually going to have a CC. Now I have 4 H's. So if you're just doing the Lewis dot diagram, you can just do them anywhere. But really, it does end up kind of angling a little bit. So I'm going to put an H here. And it doesn't really matter if you're doing the Lewis dot diagram for it. There's only one of those. Okay, we need to check our valence electrons. 2, 4, 6, 8, 10. Oh no, that's 10. The question is, where am I supposed to put the other 2 valence electrons? What do you guys think? I have 2 more valence electrons. I'm supposed to have 12. So where do you think the other 2 go? I know it can't be on the hydrogens, right?
Double
Can't
bond
do
the
it.
carbon.
It would have to be one on each of the carbons.
Which means there's
Double
probably,
bond.
together.
yes, very good. We are going to double bond it, okay? So I wanted to make sure that you guys saw that one because that does come up. And then I've got Cl2, and so we know that that's single bonds. Only nitrogen N2 is triple and oxygen is double. And then my arrow. And so now, and I do like to do this squiggly line in between, or just do an arrow in between, just to make sure that you are separating your reactants from your products. So again, I'm going to have my C's in the middle, okay? And now I have 4 H's, but I also have 2 Cl's, okay? And so the question is, where does everything go? So the way that I'm going to do this is just to try to keep symmetry right. Anybody want to guess, where am I going to put the Cl's?
On the left
Probably
and
where?
right.
Where? On the
Left and right side.
left and right. I like it. I'm going to put those on the ends, okay? Just to try to keep my symmetry right, okay? And then my hydrogens, because I still want my carbons in the middle, I'm going to put my hydrogens 1, 2, 3, and 4 of those right in there, okay? Now let's do our dots. So I've got 26. So 2, 4, 6, 8, 10, 12, 14. Hydrogens are fine. 16, 18, 20, 22, 24, 26. We're good. All single bonded. Okay. And then again, we're going to go through and we're going to total all of this. So I have 1, 2, 3, 4 CH bonds that I see. And then I have 1 of the C double bond C. And then over here, I just have 1 of the Cl, Cl. And then here I have 1 CC. And then I have 1, 2, 3, 4 of the CHs. And then 2 of the CCLs. So just make sure you don't forget the central one, okay? Because that tends to happen on like a quiz or a test, or like the exam is like people forget the one in the middle. So don't forget the one in the middle, okay? All right, and let's get our numbers going here. So the CH, do it so that I can kind of see these both. The CH, I'm seeing a 412. The C double bond C is a 612. The ClCl is a 242. And then my CC is 348. CH is 412. And CCl is 338. Okay, go for it. Let's get you to calculate this now. Okay, I believe you're gonna get an answer that is in the negative 100 something. I believe it's gonna be something negative 100 something is gonna be your final answer. If somebody ends up figuring it out first,
Is it negative 762?
I have like a negative 100 and
Oh,
something.
100. You mean like literally in the 100s?
Yes, in the
I
100.
got negative 170.
That's what I got.
Negative 170?
Oh, I missed a bond. My bad.
No problem. Is that what
Yeah.
we're getting? Because I have a different answer written down, but maybe
I got negative 170.
negative 170?
48.
I got negative 148.
Yeah, that's what I got.
Yeah,
I
I got a different answer. I got negative 148 kilojoules. Okay, so let's make sure that you used, and I'm assuming, whoever got the negative 148, because I wonder if my numbers, let me just try this real quick, because I wonder if I had used the numbers in your table instead of these numbers when I did it. So 4 times 4, 12, plus 612, plus 242, minus 348, minus.
I redid it and got negative 148 also.
Oh, you did? Okay, minus 2 times 338. No, I got, so I wonder if there's one of the numbers that I did incorrectly too, because I just got the negative 170,
You know,
so.
the numbers on the bond. on the
Yes, are a little bit different, right?
Yeah, it's like
Okay,
4,
perfect.
16,
So-
and like 614 instead of 612 and stuff.
Okay, awesome. So you may have gotten negative 170 if you're using these numbers. That's exactly right. If you're using the numbers that's on your chart, then you're going to get negative 148. Okay, awesome. Very good, you guys. Okay, and that is it for our bond enthalpy notes. So now we should be able to go into the packet to work on problems that are going to be just like this. All right. Okay, so happy day to those of you that are watching from home.